MAWLS is the multi-axis wind load simulator, and its purpose is to recreate the buffeting load conditions and the suction loads that happen on the sides of buildings during extreme winds.
Not only can we impose out-of-plane pressure to the wall system, but we can also impose vertical forces that would mimic, say, the gravity loads from the rest of the structure. And what's so special about the MAWLS is really the scale at which we can do these experiments.
The MAWLS is one of the 5 apparatus that's under what we call the NHERI umbrella. NHERI is the Natural Hazards Research Engineering Infrastructure. It's a National Science Foundation sponsored facility.
So we have 2 identical walls constructed exactly the same way. The wall on the left here has no reinforcement. The wall on the right here has reinforcement in it, vertical reinforcement and horizontal reinforcement. So what we're going to do is we're going to blow up the box, we're going to fill it up with air and try to push these walls out. One interesting thing that we could do with the MAWLS here is to come back and retrofit a unreinforced masonry wall and see how well that behaves and see if we can do that with existing buildings out there. So we have a non-contact displacement measurement system here. That's what the speckles on the surface are here.
What we do with stereo cameras, we track those dots through the entire deformation process. So it's like having thousands and thousands of little sensors, and we track the movement of all those sensors simultaneously.
And it's really important to be able to measure displacement because there's really 2 things we get out of this test. One is how much pressure can the wall hold, and then number 2 is how much movement do we get and where is that movement happening.
Okay, engaging fudge.
Yep.
Okay, we're at 1200. Can you do a countdown for recording? Ask Alex if he's ready to record.
Yeah, he's recording.
Okay.
5, 4, 3, 2, 1.
There we go. Nicely done. The wall had failed. The unreinforced masonry wall failed, as you might expect. So the wall cracked at about mid-height, which is expected, and bowed out slightly and then completely collapsed upon itself down to the floor. The load that the wall collapsed was a little bit higher than I was expecting. However, I did see cracking at a lower load. So we were at around 50 pounds per square foot when the wall collapsed, but I did see fairly large cracking at around 20 pounds per square foot. What I'm looking for is mostly on the reinforced wall. I want to see what kind of displacements we had at the larger loads, and I want to see if we can determine cracking and where cracking occurred with the remote sensing equipment. So that's really the thing I'm looking for here. So a couple of weeks ago, we tested the counterpart to this, which was unreinforced. The reinforced masonry wall has the cells filled with grouts, and inside the cells we have reinforcing steel. Today we've blocked out where the hole that's remaining from the unreinforced wall, and we're going to increase the pressure until we fail this wall. Okay, so here we are post-test, and as you can see, not much happened to the wall. The wall's still in place. Once we started loading the wall, we took it to 135 pounds per square foot, and up at that load, we measured about 1 inch of displacement at the mid-height of the wall, which is a lot for a wall like this. So there's some interesting things that we'll be able to learn here.
The reality is we can't wait till the next hurricane to get the information we need. So we need controlled environments to put the pieces together.
The idea is to get the unassailable science. Right? So the people that work on advancing our building codes, and make those decisions based on what we can learn in a laboratory like this. So this is the horse's mouth information that shows if you do this, if you build it this way, it will make it much stronger.
At the end of the day, it's about making safer structures, and when we can see how structures fail, it gives us insight into how that failure happens, and when we better understand the failure, we can better understand how to make them stronger in the future.